Hello students, today we will summarize our chapter. The chapter we have read so far is electric charges and field, and in this we have covered up the 14 topics so far, like the introduction to the chapter, natural phenomena which we are seeing on the daily basis, where we experience electric currents, then the definition of electric charges, their polarity, and why these few items or the few things, few objects are able to conduct the electricity and others are not able to conduct. Like when we take example of iron rod or steel bar, they are able to conduct, whereas wood and plastic cannot conduct electricity. So it is based on their properties. The objects which are able to conduct are called conductors, whereas the objects which are not able to conduct are called insulators. And we have read about the third class also in this third class of elemental classification, that is the semiconductor, which on the normal way do not conduct, but under the special conditions they do conduct. Like if we are introducing doping or increasing the temperature, they will become conducting. Then we have read the basic properties of charge, like additive properties, superimposition principle, okay, and conservation of the charges, how we are adding and how these charges are being conserved. Then we have read the Coulomb's law. This Coulomb's law gave us the force. This Coulomb's law helped us to define force for the given charges, Then we try to understand if there are not only two charges present, Q1 and Q2, but a series of charges, a system of charges are present, like Q1, Q2, Q3 and Qn. At this point, how we are applying the Coulomb's law we have understood under the topic force between multiple charges. Then we introduce the concept of electric field. Electric field is a advanced concept here. Apart from Coulomb's law and superposition principle, this concept is applied for the electric charges to define them very much properly and to define these electric charges at each and every point in discrete system as well as in continuous system. We have learnt about the electric field lines, how they are, what are their properties, and how we can define the charges with the help of electric field lines. Then we learnt about the electric flux, which is the electric field line coming out from a surface, coming out from a given surface, which is a associated topic with electric fields. Then we read about the electric dipole, how it is made and why the electric dipole is called so, as it have charges having same magnitude, but the polarity is being changed, but opposite polarity, and hence they make a dipole, like minus q plus q have a like distance of 2a or set apart by a distance of 2a will constitute a electric dipole. Properties of that electric dipole and how this dipole behaves in the uniform electric field. Then we learn the continuous charge distribution at these level of macroscopic level, where everything is big. In this big world, these charges tend to seem like a bag of these things. They are not discrete but a continuous trail, like this. Starting from here, this is the continuous trail of charges, and all the charges are present inside this. So they are not like discrete units, Q1 over here, Q2 over here, Q3 over here. They are not like this. We cannot segregate these charges. At a point, we need to understand the continuous charge distribution. Under this topic, we have found that Coulomb's law and superposition principle both are applicable for the continuous charge distribution also. Then we read about the Gauss's law. The Gauss's law defines electric field line associated with the given surface area, and hence gives us the value of flux. Under the topic of application of Gauss's law, we have seen electric field produced due to a wire of infinite length, a planar sheet, and a spherical shell. So these were the things we have read under the chapter electric charges and fields, and in this today's class we will be summarizing everything in the same class. Okay, so that we will be going for a recap and refreshing our memory what we have learned so far. So the summary starts. Electric and magnetic force determine properties of atoms, molecules, and the bulk matter. These electric magnetic forces which are present for the given atoms, the molecules, or any other sort of bulk material like a iron rod or a plastic chair, they determine these properties, their properties. Like how can we determine a wooden piece is different from a plastic piece, and how these two are different from an iron bar or an aluminium bar. So these two things do not produce any electric or magnetic field lines, but iron and aluminium do produce. So this is one of the characteristic property which differentiates these two, and hence provides and determines few properties of the atoms, the molecules, and the bulk material. The molecules, we have seen the molecule like water H2O and the molecules like CH4. What is the difference in these two? H2O is a polar molecule. Under the absence of electric field, these two shows polarity. Oxygen is having negative polarity, whereas hydrogen have a positive polarity. But when we talk about methane, it is a non-polar molecule. Non-polar. Under the effect of electric field, there will be the differentiation of electronegativity of carbon from the hydrogen, but generally this is a neutral and do not have any sort of polarity existing in this molecule. So these are the small things which are electrical and magnetical in nature and determine their properties. Now the point number 2. From simple experiment on frictional electricity, one can infer that there are two types of charges in nature. How many types of charges are there? Two types. And that like charges repel and unlike charges attract. By convention, the charge on a glass rod rubbed with the silk is positive. That on a plastic rod rubbed with the fur is negative. So we have seen the frictional electricity, and from that, as we have read while we were reading about the properties of the charges, how we have differentiated, we did a lots and lots of experiment to define that charges exist in two polarity, one positive and other one negative. And we have seen that when we are rubbing silk with glass rod, this glass rod attracts positive charge. This glass rod gets positive charge, but the opposite is seen when the plastic is rubbed with fur. The plastic gains negative charge. What does it mean? It means that fur have the negative charge which is delivered, which is transferred to the plastic, or the plastic is having the positive charge which is being transferred to the fur, or vice versa. So removal or addition both can make a element charged. Both can make a element or an object charged. Third one, conductors allow movement of electric charges through them. Insulators do not. In metals, the mobile charges are electron, and in electrolytes both positive and negative ions are mobile. So when we aim at understanding the metals have electrons on their surface. So this is a surface of metal, and these electrons are present over here and they are free to move. Hence, whenever excess of electrons are provided or charge is provided, these other electrons move from this end to this end, conducting these charges from point A to point B, showing the conduction. Whereas when we talk about electrolytes, first thing we should know what is electrolyte. Electrolyte is a solution where while adding solute to the solvent, we have got the ionization happened in the solution. Like if we take water, we will see this water have polarity of H plus and OH minus. So when we aim at conducting electricity, the H plus will move to the negative charged of the battery, whereas OH will tend to move to the positive charge of the battery. Hence they will conduct the electricity. So in an electrolyte, both positive and negative ions are mobile, but in metal only electrons show mobility. Point number 4. Electric charge has three basic properties: quantization, additivity, and conservation. Quantization of electric charge means total charge Q of a body is always an integral multiple of basic quantum of the charge, that is Q equals to NE, where N can be 0, plus minus 1, plus minus 2 up to plus minus infinity. Proton and electron have charges plus E and minus E respectively. For macroscopic charges, for which N is a very large number, quantization of charge can be ignored. This can be ignored at macroscopic level. So, quantization is Q equals to NE, integral multiple of the charges. E for proton is plus E, and E for electron is minus E. Value of E is 1.6 into 10 to the power minus 19 coulombs. So E's SI unit is coulomb, hence the charge's SI unit is also coulomb. Additivity of electric charges means that the total charge of a system is algebraic sum, that is the sum taking into account proper sign of all individual charges in the system. Conservation, the electric charges means, conservation of electric charges means that the total charge of an isolated system remains unchanged with time. This means that when bodies are charged through friction, there is a transfer of electric charges from one body to another, but no creation or no destruction of charges happens. So charges neither created nor destroyed in a isolated system. In an isolated system. Now, Coulomb's law. Point number 5, Coulomb's law. The mutual electrostatic forces between 2-point charges Q1 and Q2 is proportional to the product Q1 Q2 and inversely proportional to the square of the distance between them or distance separating them. Mathematically, F21 force on Q2 due to Q1 is given as KQ1 Q2 by R21 square into R21 cap, where R cap is a unit vector. Unit vector for the distance between Q1 and Q2. Where R21 is a unit vector in the direction from Q1 to Q2 and K equals to 1 upon 4 pi epsilon naught, that is a constant of proportionality, and value of K is given as 9 into 10 to the power 9 Newton meter square Coulomb to the power minus 2. In SI unit, the unit of charge is Coulomb. We have seen previously charge is in coulombs. Experimental value of the constant epsilon naught is 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. And it is very much important to remember the value of epsilon naught, that is 8.854 into 10 to the power 12, and the units are all opposite to the value we have got for the K. It is Coulomb square Newton inverse meter inverse square. ठीक है? SI units are very much important for one to learn, and SI units many a time helps us to solve a numerical also. Next time whenever we are solving a numerical, I'll explain how the SI unit have played a very much important role in it. So one should always make sure that they are learning the SI units along with the formulas too. Now the sixth point, the ratio of electric force and gravitational force between a proton and the electron is given by Ke square GME MP, which is approximately 2.4 into 10 to the power 39. Here this particular statement actually states that electrostatic force equals to 10 to the power 39 times gravitational force. Electrostatic force is stronger than gravitational force by a factor of 10 to the power 39. Now superposition principle. Superposition principle and Coulomb's law are very much important when we deal with electrostatics, electric charges and electric fields. The principle is based on the property that forces with which two charges attract or repel each other are not affected by the presence of third charge. For an assembly of charges Q1, Q2, Q3, the forces on any charge, say Q1, is the vector sum of forces on Q1 due to Q2, forces on Q1 due to Q3, and so on. For each pair, the forces is given by the Coulomb's law for the two charges stated earlier. Here the statement says that when we are dealing with the superposition principle, we aim at defining the system of charges. What exactly happens over here is, in this system of charges, there will be a lot of systems present here, like a Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, and so on. So we have a system of charges having these many charges. Okay, and so on up to Qn. Now what exactly happens is, in general what we see is a charge over here will be influenced from the charges placed all around it. But according to superposition principle, the same scenario is not followed. We find force on the charge 1 due to charge 2, like Q1 and Q2. Then we find force on 1 due to charge 3, then on force on 1 due to 4. Similarly, force on the first charge due to nth charge. Then we add up to get the total force on charge 1. We add up all these values, F12, F13 up to F1n. We add all these, so this thing gives us the total charge, and this particular formula is termed as superposition principle. Now the 8th statement over here, it says electric field E at a point due to charged configuration is the force on a small positive test charge Q placed at the point divided by the magnitude of the charge. Electric field due to the point charge Q has a magnitude of Q modulus by 4 pi epsilon naught r square. It's radially outward for the Q if Q is positive, and radially inward if the Q is negative. Like Coulomb's force, electric field also satisfies superposition principle. What does it say here is that for this electric field concept, we are having a charge capital Q, and this charge is in a system. Now from the infinity we are bringing this small charge Q here at a distance of r from the capital charge. Now this force we give as QQ by r square into the constant K. Now for giving us the electric field, what we do is we divide our force by the charge which is being placed here. So it will give us force on the charge, test charge. Test charge we will write as Qt, so it is very much explanatory, Qt. So the electric field will be given as K capital Q upon r square. Electric field due to the capital Q charge at a distance of r square. That is the value. If our Q equals to positive, then they are outward, away from the charge Q. This is positive charge. If the charge is negative, they tend to come inward. So they are radially inward. This is very much important. Like the one statement we have read, like charges repel, like repel, unlike attract. Similar way, one should mug this up or always keep this in mind, that if the charge is positive, the field lines move away from it. If the charge is negative, field lines tends to move towards the charge. They have inward, radial inward motion. Now coming to the point number 9, an electric field line is a curve drawn in such a way that the tangent at each point on the curve gives the direction of electric field at that point. The direction of electric field is not given by the electric field lines. The electric field lines which we draw are the tangents to each and every point to the curvicle line. See, this is the curvicle line and we are making a tangent over here. So the tangent to this point is this. This is our electric field line. So this tangent is giving us the direction of this electric field line. Similarly, if we have another electric field line like this, the tangent over this will give us electric field for direction of this electric field. This is electric field 1, this is electric field 2. So this is the direction for 1, this is the direction for 2, and it is given by the tangent. The relative closeness of the field lines indicates relative strength of the electric field at different points. They crowd near each other in the regions of strong electric field and are far apart where the electric field is weak. In regions of constant electric field, the field lines are uniformly spaced at parallel straight lines. So what does it say is that if the field lines are moving away from each other, they are not having uniform uniform separation. Like, see, they are not uniform over here. So these lines here are nearer to each other, here they are farther from each other. So nearer implies they have higher strength at this point and a lower strength at this point. And when we say our field lines are uniform in nature, uniform, that implies these electric field lines are parallel to each other and equidistant and at equidistance. So electric field lines have their own significance. By the crowd of electric field lines and by their separation, we can find out their relative strength in a given point. So the 10th point over here, some of the important properties of field lines are continuous curves. They do not break without any break. Field lines cannot cross each other. Why they cannot cross each other? Because if, like, this is our field line and this is our another field line, in this case we are making a tangent from here. This gives the property of this field line. We make another tangent over here and this gives properties of this field line. Now if they are crossing each other, that implies these two are not the proper field lines and they do not have their unique direction. It will look absurd. Like this kind of motion of the field lines have no meaning, and through the experimental visualization we have found that no such cases do exist also. Electrostatic field lines start at the positive charges and end at the negative charges. They cannot form the closed loops. They do not form. If, see, this is, just a minute, this is our positive charge, this is our negative charge. Okay, this gives us fields which are radially outward and they will go to the negative charge. So radially outward electric fields are produced by positive charge and radially inward near the negative charge. Now in the uniform surface we have only positive charge. It will give us these rays which are outward, which are radially outward. The condition is being satisfied, but they will end at infinity. They will keep on going. If there is no negative charge in the system, these field lines keep on going and will meet at infinity only. So they do not form any closed loop. No closed loop. Now one question you can say that this is there from here to here, this is becoming like a closed loop. No, Closed loop implies something which is emerging from the same point and ending at the same point. Are these lines emerging from the positive end and ending in the positive charge? No, they are emerging in the positive charge, but they are ending up in the negative charge. Hence, these are not forming any closed loop. Coming to the 11th point. An electric dipole is a pair of equal and opposite charges Q1 plus Q and minus Q. They are equal and opposite as explained already. Equal magnitude but opposite polarity. Okay. Now, separated by some distance 2a, its dipole moment vector P has a magnitude equals to 2qa. That is distance into the distance between the two charges and the magnitude of that charge is in the direction of the dipole axis from minus q to plus q. Electric field tends to move from minus q to plus q. Field of an electric dipole in its equatorial plane, that is plane perpendicular to its axis and passing through its center at the distance r from the center is given by this equation. Electric field, that is a vector, into gives minus of P. P is our dipole moment. Dipole moment. And value of P is given as 2aq, where 2a equals to distance between minus q and plus q, and q is the magnitude of charges. Okay, and as it is equatorial plane, this is our charge minus q, this is our plus q. Electric field line moves in this direction. This is equatorial point, and so from this equatorial point this whole is 2a. If we are divide this, it will be a, and this length is r. R distance from the center of the dipole. So this distance, this particular distance will be coming around under root a square plus r square. So we have introduced over here. First thing was, for the electric field, what we have, q upon r square, k into q upon r square. So here r square is this value. We will substitute this, and for the P also we will have some value, and here the electric dipole will be given in this direction. Electric field resultant will be in this direction, because from this charge electric field will come to this point, and from this charge it will go to this point. Okay, so electric field will be here, not this way. If we are taking positive charge here and negative charge here, the electric field will be in this direction. So E resultant will be here. From this diagram we can derive it, and we have already derived it while we were reading about this concept in our previous classes. So for the derivation you can go and check it. Now when we are having a case where our A dipole is extremely small, our dipole is extremely small, the distance A is smaller than the R, or the R is much bigger than A. This equatorial point is very much away from the center of equatorial point, away from the center of dipole. Like dipole is just 2 mm and our equatorial plane is something like 20 centimeters. So this is very much far away. In such a case, this a square will reduce to 0, because it will have some negligible value. which can be ignored. So in this concept we are ignoring the squared value or the powered values. Not like if in case of P we are writing 2AQ, we will not ignore this A because this A do not have power. Any small value when powered will become more small. That's why we are removing this powered value only, and we will get a equation like this. I'll write over here E equals to P vector divided by 4 pi epsilon naught into r cube. Now this electric field for a dipole is directly proportional to 1 by r cube. Here in the case of dipole, equatorial dipole or the axial dipole, these are dependent upon 1 by r cube. They have relation of 1 by r cube, not 1 by r, not 1 by r square. This is like a favorite question of the entrance examination. In the entrance examination, they will give you a graph like this, where they will ask you, tell us the graph for electric fields for a spherical shell, electric field for a solid shell. This is for the spherical shell and this is for the solid sphere. And when they ask you what is the relation between the electric field of a dipole with distance, with equatorial or axial, any distance, okay, with distance. So you don't have to give us in general like electric field equals to kq by r square. So in general it is dependent on r square, but in case of this it is dependent upon 1 by r cube. I am highlighting it once again just because I know most of the students make issues in this. Many a time I have seen students creating a rukas whenever they see this question, and they always go by 1 by r square. Whatever the case is, 1 by r square relation, 1 by r square relation. But whenever dealing with the electric dipole, always remember E is proportional to 1 by r cube. Now dipole, electric field on the axis of distance r from the center is E equals to 2 pr upon 4 pi epsilon naught r square minus a square the whole square. Solving it, we will get 2p by 4 pi epsilon naught r cube. The same, we have taken r is much greater than a. In the same case, again we have found that electric field is proportional to 1 by r cube. Now the 1 by r cube dependence of the dipole electric fields should be noted in contrast to the 1 by r square dependence of the electric field due to a point charge. 13th, in a uniform electric field E, a dipole experiences a torque of tau given by tau equals to P cross E, but experiences no net force. The net force over a torque is 0. I'll explain it. This is our minus q plus q. What do you think is this? This is our dipole. Now we have these electric field lines and they are uniform, so they will be parallel and equidistant from each other. These are uniform. Now these uniform, these will try to align this dipole along with them. Electric field will try to align dipole moment P along with it. E and P should be parallel, having a theta of 0 degree. Okay, they will try that. So to try that, this will move downwards. The force over here will be QE, and this will tend to move upwards, and the force over here will be minus QE. So when we add the forces on 1 and forces on 2, they are equal and opposite. Equal and opposite. But entirely the system do not face any force. No force, no net force on the entire system. So after this QE, this force and this force struggles and brings this, aligns this with the electric field, this dipole becomes stable unless until they experience a torque tau. This torque tau is given by dipole moment P cross E. It is a vector quantity. These all are vector quantity, and we can write this as PE sin theta. So see, sin theta, if theta is, we are aiming at understanding sin theta. Theta can be 0, theta can be 90. So when theta is 0, the value will come 0. So torque will be 0. Torque will be 0 implies that P and E are aligned with each other. But when theta equals to 90, the torque will be 1. That is maximum, that is P equals to E, that is maximum torque. That will happen when our electric field is moving in this direction and the electric dipole's moment is in this direction. So they are at 90 degree to each other. At this point, the maximum torque they will face. There will be a whole lot of force which will try to make P and E in the same direction. Moving on to the next. Flux. The flux del xi of electric field E through a small area element of del S is given by del xi equals to E into del S. Small flux equals to E into the small area. The vector area del S can be given as del S equals to del S into N. Here this is a vector quantity and this is not a vector representation because we are adding a unit vector which will provide us the direction. So del S bar equals to del S into this. So this is a vector representation, this is a vector representation, where del S is the magnitude of the area element and N is the normal to the area element, which can be considered planar for sufficient small areas like del S. For the area element of a closed surface, now we are considering a closed surface, and for that we have taken a area element. N is taken to be direction of outward normal. In this closed, we do not take the direction inside it but outside. See, this is our sphere of some containing some charge. For this sphere, the values which we will take, the direction which we will take will be from inside to outside, from inside to outside. So that's how we are going to take. By convention, this is taken. Now Gauss's law. The flux of electric field through any closed surface S is 1 by epsilon naught times the total charge enclosed by the surface area. The law is especially useful in determining electric fields E when the source distribution has a simple symmetry. This Gauss's law is used whenever we are having the symmetric distribution of charge. We can use the Gauss's law over there. We can make a Gaussian surface and find what? We can find electric field using the Gauss's law. where now we have taken three simple cases. These are the application of Gauss's law. We have taken a thin infinitely long straight wire of uniform linear charge density, that is lambda, and it gives us a electric field of E equals to lambda upon 2 pi epsilon naught r into n vector, where r is the perpendicular distance of the point from the wire and n is the radial unit vector in the plane normal to the wire passing through the point. Next, we have taken an infinite thin plane sheet of uniform surface charge density, that is sigma, and then the electric field due to that uniform sheet will come around E equals to sigma by 2 epsilon naught into r into n cap. Then we have taken the last Gauss's application, thin spherical shell. Shells are hollow from inside, hollow. They are not solid spheres, so they have a different property when compared with the solids. Of uniform surface charge density sigma. Here E equals to Q by 4 pi epsilon naught r square into r cap, where r is bigger than capital R. The radius of, I'll make a diagram over here. This is our shell and this is our radius capital R, and then we have taken the shell with a radius small r. So this is our Gaussian surface. This is our Gaussian surface. We are defining for this surface. Okay. We are defining for this surface. This blue in color is our Gaussian surface. Now this one point here, if I take, this is our another Gaussian surface which is also having a value of r, radius is r, but this is inside, okay. So at this point also we are aiming to find electric field, and at this point also we are aiming to find electric field. So E equals to 0 when r is smaller than capital R, when the radius of Gaussian surface is lesser than the radius of our spherical shell. Now how that is justified, let's see. The electric field outside the shell is as though a total charge is concentrated at the center. Electric field when we aim at the outside of the shell seems like concentrated at the center. The same result is true for the solid sphere of uniform volume charge density. The field is 0 at all points inside the shell, and there is no such justification given, so I'll justify it for you. And it is like inside the shell there is no charge distribution, as it is a shell. This is a empty space. This is a empty space. So the where will be charge going? Charge will be over here on the surface. So when we are taking a Gaussian surface smaller than this shell, then there will be no charge enclosed by the Gaussian surface. I'll write over here Gaussian surface having radius r smaller than capital R contains no charge or encloses no charge. Hence E equals to 0 in that Gaussian surface. That's how it's justifiable. But if it is a solid sphere, then the whole scenario will change, and we will have some electric field inside the solid sphere. Now before moving to these physical quantities and their dimensions, unit symbols, I'll explain you one more concept. This is our shell and this is our solid sphere. Solid sphere. Okay. This is our solid sphere. Solid sphere have mass distributed all over the sphere, whereas what about this shell? There is no mass inside. Now the electric field lines are coming. Electric field lines are coming from here. They will go here and then will come out. Now they will come here, then they will tend to meet the center and then they will come out. Then again some are coming, they will tend to meet and then they will come out. Similarly from here they will go, tend to meet and will come out. Go here, tend to meet at center and come out. This is the electric field distribution for a shell. No electric field lines will be available inside the shell. But when we deal with the solid sphere, we will see electric field lines coming like this, coming like this, coming like this, and then like this. Okay, this is how the electric field lines appear in a solid sphere. Now we will move to the next topic, that is understanding the physical quantities, their symbols, their dimensions, their units, and some important remarks if any exist. The vector area element is del S. This del S is a vector element. It is given as del S with a arrow. As this is an area vector, it have a unit of meter square. As it is a meter square, it shows the length and hence the dimensions are L2. Dimensions are always are in the square brackets. To remove, like to make it scalar, we can make this vector area equals to scalar area into the unit vector. We can introduce the unit vector because unit vector provides the direction, and in a vector quantity what we need only direction and magnitude. The del S component, which is over here, will give us magnitude of the surface area, and this will provide us the direction. Now the other one is electric field. It is denoted by E, capital E, and this capital E with a arrow denotes the vectoral property of the electric field. Electric field have a unit of volt per meter, and it have a dimension of mass, length, time to the power minus 3 and ampere inverse. Electric flux denoted by Xi, and its unit is volt meter. This electric flux according to the Gauss's law is given as Q upon epsilon naught, and by the derivation of electric field this is given as E into S. These both E and S are vector, and hence they can give us E S cos theta. Now dipole moment in a dipole is directed from minus q to plus q, and it is denoted by small p with a vector head vector arrow. It have a dimension of LTA, length, time and ampere or charge, with a unit of coulomb meter, vector directed from negative to positive charge. Now charge densities. Charge densities are of three type: 1, 2 and 3. Linear, defined for a line mass, surface for area, and volume for some solid three-dimensional structures where volume plays an important role. For linear it is defined by lambda, for surface it is defined by sigma, and for volume it is defined by rho. So linear is given as lambda equals to q upon del L, surface is given as sigma equals to q into del S, and volumetric is given as rho equals to q upon del V. So here the SI unit is coulomb per meter, here coulomb per meter square, and here coulomb per meter cube. So accordingly you can see the dimension will come LTA, where L will be in negative value because this is in negative, same LTA, but here there are 2 powers, so -2. Similarly here there are 3 powers, L minus 3 Ta. Okay, so this is the charge densities dimensional formulas, and see here we have in the remarks we have provided you the formulas also. Charge upon length, linear charge density, charge upon area, surface charge density, and charge upon volume will give us volumetric charge density. So this is all what we have seen in our chapter electric field and charges. Now, like electric charges and fields, that is the name of the chapter, which is the first chapter here in the physics book, and it is quite important, which deals with all the static charges in our system, how these charges influence, and they are not exactly static. If all the charges are static, it's very much different and difficult to produce the electric current. Electric current is a property of charges in motion. So when we, like in this concept where we have dealt with many things, we have learnt the properties of charges, and how they are added up, what are the other factors which influence these charges, all these things. So I will just give you the tips where you have to take care of whenever you are reading in this in the next slide, and in the next class we will see some points which need to be pondered upon, which needs to be read once again to understand or to memorize it, which are quite important as per to the NCERT, right? So just a minute, I'll just tell you the few tips where you need to pay a little more attention, little more focus is needed on it. Or I'm just thinking, like after reading the points to ponder, we will deal with the tips and the tricks to read this chapter and to stress out where we need to understand the important topics. So we'll end up today's class at this note, where we have understood the physical quantities, symbols, dimensions and their units. And this is also a very important table, mark it important and note down it in your notebooks, make it in your notebooks and read it on a daily basis. Like in your entrance examination, there are questions based on this, questions based on dimensions. So make sure that you are understanding a formula. Once you know the formula of a physical quantity, if you know the formula of physical quantity, it's very much simple to find out the dimensions. Okay, and these dimensions play a very much important role in understanding how they are influencing the length, mass, time or any other factor associated with them. So this is a very much important and we can say a favorite question of the entrance examination. So please kindly pay attention to this particular table. And that's all for today's class. We'll meet in the next class with the topic of points to ponder, and then I'll give you some tips and tricks and the points where you need to pay little more attention to understand this subject properly. So bye bye and have a very good day.